Hello and welcome to a new video for Precalculus Math UC. This is double angle and half angle identities, the last of our identities. So if you were wondering if it was going to be never ending, we are at the end. After this lesson, there aren't any more new identities for us this year, okay? Not saying that there maybe aren't more if you go on to do more math, but at least for us right now, this will be our last lesson. So let's take a look at these identities. So starting with the double angle identities, if you think about what double means twice as much. So this situation is going to be where if we break down what the angle is inside of here, it's actually twice as much as some other angle that hopefully we know information about. Now, this is a weird one because as far as special right triangles go, we know things like 30, 45, 60. We also know all the doubles of those. Like if you double 30 and get 60, we also can find sine of 60 just fine using the same method that we use for sine of 30. So this ends up being more relevant to if we maybe know something about the triangle that has an angle of A and want information about 2A. I don't know, it's kind of weird. We also have this whole thing with identities that part of it is just leading us up to calculus, and in calculus what we might do is say, oh, I have cosine squared minus sine squared here. It'd be so much easier to rewrite that as cosine of 2a instead for doing the calculus-y thing. And certainly for tangent, right? If you somehow ended up with what's on the left, if you somehow ended up with what's on the right there, if you somehow ended up with that, then changing it to the left would make things simpler, right? So just throwing that out there. These are our double angle identities. Now, because cosine of 2a equals cosine squared minus sine squared, and because of the Pythagorean identities that say cosine squared plus sine squared equals 1, we actually have two other versions right here of cosine 2a that we can get by kind of like rearranging and making replacements in that identity. So that's why there are three different ones. So you would decide which one to use based on what information you know. If you know cosine and sine, you can use the first one. If you just knew sine of something, you could use the second one. If you just knew cosine, you'd use the third one. Let's look at half angle identities. Now these we actually can use to find things with the help of our unit circle, things like 15 degrees, which is half of 30, because we would put this in and say that b is 30, so sine of 30 over 2, which is 15, equals, and then we'd fill in 30 right here where b is, and since we can find cosine of 30, we can get a mostly unsatisfying answer because it will end up possibly being a square root under a square root, which is just not nice. On these that have plus and minus signs here, by the way, it's not saying plus or minus as in it's both, like we're used to with the quadratic formula. It's saying plus or minus because we actually have to figure out whether it should be positive or negative based on the information we're given. So for instance, if we are asked to find sine of 15 degrees, sine of anything in the first quadrant is positive, so we would choose positive square root of 1 minus cosine b over 2. So we're not saying it's both, we're saying it's one or the other. Tangent on this one has three things it can be, not cosine. And if you're interested in knowing how any of these identities came about, the double angle ones are actually really easy to get from the sum and difference identities. And then the half angle identities, I don't know if I even know how to get those. I know that to get the second and third one for tangent, it involves rationalizing the first one with square roots, which just sounds like a hoot and a half. So we won't be doing that because I can only stand one hoot at a time. So let's go ahead and look at some problems like what we might see. Evaluate using the half angle identities in your calculator if necessary. Okay, so by the way, as we're looking at these, doing the, I tried to say this earlier, but doing the double angle identities is kind of pointless almost in a way. Like, find sine of 60 by using the fact that that's double of 30. To me, that's frustrating. Like, to know that I could have just done it easier. I'm sure that's frustrating to you as well. So when you see that, use your judgment. If you want to use the double angle identity to do that, go for it. But here for the half angle identity, we do in fact need to use the half angle identity if we want to get something instead of just plugging it into our calculator, which I'm sure some of us would rather do anyway. Okay, so the sum and difference identity for sine is plus or minus, but because it's 15 degrees and the first quadrant is all positive, it'll be a positive square root. Sine is 1 minus cosine? Sine is 1 minus cosine of b over 2. Now here's the thing that can be tricky. This is sine of b over 2. What we have is 15. So what over 2 equals 15? That would be 30. So in this, I'm going to replace b with 30 and then work this out. So let's think. We don't really need the plus in front of the square root. Let's think about 30 degrees and cosine of 30 degrees more specifically. Here's 30. Cosine is adjacent over hypotenuse, so that's square root of 3 over 2. So we're going to do 1 minus square root of 3 over 2 over 2. Now here's the simplification that we can go through, is we can say, okay, let me get a common denominator on top. To me, this is the worst part of the problem. Okay, common denominator on top, so 2 over 2 minus square root of 3 over 2 over 2 over 1. So now that becomes 2 minus square root of 3 over 2 over 2 over 1. Now we've got a fraction over a fraction, so we can flip the bottom fraction and multiply by a half, because that's what we do when we divide fractions. So that's going to make the bottom be 4. So 2 minus the square root of 3 over 4. Well, we can take the square root of 4 and get 2. So we could then put this as 2 minus the square root of 3 over 2. And to me, that is kind of our best answer, our best looking answer. I guess maybe equally good would be to actually take the 2 and put it in front as a half. That's something else we can do. We could do this, but we basically can't get rid of the fact, as far as I know, we can't get rid of the fact that there's a square root under a square root. It's just unfortunate that it's going to look like that. Now, all of these, in a similar way to the sum and difference identities, we're going to see similar answers here. Not similar answers to the sum and difference identities, similar answers to each other. So for instance, we're going to do cosine of 15 degrees, and it's going to, I guess, work out nicer because it's cosine. No, it's going to work out very similar. I just realized. So 15 degrees, again, is in the first quadrant, so positive. This one is 1 plus cosine b. It's so interesting, right, that the only difference between the two is that sine has a minus and cosine has a plus, right? Again, b is 30, so we're going to do 1 plus cosine of 30 degrees over 2. We just said cosine of 30 was square root of 3 over 2. So this is going to look the exact same, but with a plus sign in the middle instead of a minus sign. So you could probably pretty easily look back at your work and go, okay, well then all of this is going to be the same, right? And I'm just going to end up with the same thing, but with a plus sign instead of a minus sign. So not the exact same. But the process we went through was getting a common denominator, putting the top together as one fraction, multiplying by the reciprocal. I'm going through it again in case, I'm going through it fast, but probably isn't helpful, but going through it again for those of you who are like, I'm still confused. 2 times 2 on bottom is 4. We can square root the 4 on bottom. We can't square root the top though, so we are basically separating them out. And see how similar that is to the answer we just got for example 1. So how about if we do tangent? Now, you might be thinking, there's 3 choices. How do I pick which one to use for tangent? And the same issue would come up on cosine for the double angle identities as well. So let's look at the half angle identities. So my strongest feelings on this is avoid the square root one unless you have a really good reason for using the one with the square root. And then as far as which of these two is better, I have a feeling I would likely pick incorrectly, because if it's sine and cosine, and we think about our unit circle values in particular, we maybe have like square root of 3 over 2 and 1/2. So one of them is going to have a square root no matter what. So I'd say I tend to like the idea of this one better, just because it is a single thing on the bottom of the fraction instead of 2, but really it doesn't make a huge difference. And I actually just remembered that this says to use your calculator if necessary. So I'm pretty sure that for our Math You See workbook, they're just fine with us going ahead and putting in whatever this is as a decimal. And I don't even know what it is, if I'm being honest with you. I don't know, but I can find out. And so we actually could have done this actually pretty far back and saved ourselves some pain. But where's the fun in that? So I've got 3 decimals is good, so 0.259. And I think if you look in, I looked at the answers earlier to see how they handled this. I think they actually did the decimal for cosine of 30 back here and then took that through. So that is an option, but the part of me that really likes exact value answers really doesn't like that that's how it is and would rather we go through all of this effort. On your TI calculator, you can press up twice if you typed in this to find the decimal, and just write over the minus and make it a plus. Here in Desmos, we can use our mouse and everything to do that. So this would be 0.966. Okay, now let's do tangent. So I'm going to do 1 minus cosine b over sine b. And this is still b over 2, so b is still 30. So it should be 1 minus cosine 30 over sine 30. Okay, and so we're thinking about our 30, 60, 90 triangle that has these sides. When we're proving things with the half angle or double angle identities, it's going to be a lot more important which one of them you pick of the ones that have 3. But I also think usually there's a pretty clear winner as far as like if you're looking at it and looking at what's on the other side. Hopefully there's one that makes the most sense. So this is square root of 3 over 2 for cosine 30 and 1/2 for sine 30. You can kind of see how people might memorize these because they're coming up so much. If we want to get an exact value, we'd make a common denominator on top and have 2 minus the square root of 3 over 2 over 1/2. And then we would, oh, it's over 1/2, so we would multiply by 2 over 1, which is actually going to cancel out those 2's and give us 2 minus the square root of 3. Or 0.518. So that's using the half angle identities. Let's look at one where we're using double angle identities. So this says verify that the equation is true. I know that it's using the double angle identities because of this 2 in front of my angle. So this is basically saying, if we think about it, that sine of 100 degrees equals 2 sine of 50 times cosine of 50. So how do we figure this out? We grab our calculator because we don't know anything about sine or cosine of 50. We could use trig tables, I guess, but I still haven't ever used a trig table. Kind of like to see how long that lasts. No. I'm going to make a video about it at some point. So sine of 100. Got to change to degree mode. So if you get something weird, did I change to degrees? Yes. Let me try again. I guess that is probably right. because it's a ratio of sides. So I get 0.985. So that's what this side is. Well, do we get the same thing for the other side? Okay, I double checked. This is how they want us to do this. So then we could do like, I mean, we could split these up if we wanted to, I guess. We could say 2 times sine 50 times cosine 50. No, let's not do that. Let's just do it all at the same time. So 2 sine 50 times cosine. Whoops. Oh, look at that. It's also 0.985. What are the odds of that? So 0.985 on both sides. We have verified that the equation is true. Now, if they did give us something that we could use special right triangles for, by all means, we should try to use our special right triangles. But this was not one where we could do that. Let's look at another thing they can give us as far as double angle identities go. Find sine of 2 theta and cosine 2 theta, where what we know is that sine theta is 4/5 and is in the first quadrant. So this is how we can get around the whole, like, it's ridiculous to do special right triangle angles because we could just use special right triangles to find double of whatever. This is how we get around this, because we could find theta technically by using trig tables or a calculator with this 4/5, but we can actually just use the identities for sine 2 theta and cosine 2 theta and make a triangle to help us out with this. Sine of theta is 4/5. This is not proportional. We can use the Pythagorean theorem to find the third side, or maybe we have this ratio memorized because it is special. So this would be a squared equals 9, so a equals 3. So for sine 2 theta, our formula, I like to think of these more as formulas than identities, honestly, is 2 sine theta cosine theta. So that means that sine theta for this, we already actually knew that was 4/5, and cosine theta would be 3/5 adjacent over hypotenuse. This is going to seem much more satisfying than what we did with the half-angle identities, right? So we'd do 2/1 times 4/5 times 3/5. So that would be 24/25. And that is a fraction instead of us getting a decimal, so that's nice, I guess. For cosine, we have 3 options to pick from. It really doesn't matter which one you pick. They literally will give you the same thing. And if we only had to find cosine, it would be quickest for us to use the one with sine, and then we wouldn't have even had to find the other side of the triangle. So that identity is, let me cheat. That one that uses sine is 1 minus 2 sine squared theta. So what I'm saying is, if we hadn't had to do the first one and we just had to do cosine 2 theta, we would do 1 minus 2 sine theta. It said was 4/5. We square that, work this out, and get our answer. So remember to square first and get 16/25. And then 1 minus, that would be 32. Whoa, that's not a minus sign. One minus 32/25. And then that would be 25/25. 25/25 minus 32/25 is -7/25. So there we go. That's our answer. So whatever angle goes with sine of with 4/5, which we could find that angle if we wanted to. If we double that angle, the sine of it is 24/25, and cosine of it is -7/25. I think that's actually kind of cool, now that we think about it, but hey, it's whatever. Finally, example 6. We're going to prove that the following expression is an identity. It looks like this one uses our double angle identities. and we're just gonna see how it goes. It looks to me like the right side might be more helpful to change here at the beginning, because cosine has 3 options, and so I would like to kind of know more about what I think is going to happen here. I'm going to change cosine to cosine over sine. I'm going to change sine 2 theta to its identity, which is 2 sine theta cosine theta. I need to mention here, remember that our angles have to be the same, like to cancel out. So if I left it as sine 2 theta and distributed cosine over sine 2 theta and sine theta don't cancel out. That's not it. Sine 2 theta and sine theta don't cancel out because they're not the same. That would be like saying sine of 60 cancels out with sine of 30, right? So we can't cancel those. That's why we're going to change it using the identity. Then minus tangent is sine over cosine. And then I think our next step here is to distribute, right? So for this one, let's see, we cancel out a sine and we combine cosine, so we get 2 cosine squared. And then when we do this one, now the sine isn't really canceled out, right? Because it canceled out this sine, but it's still there to distribute to this one. Oh, cotangent times tangent should be 1 because they're reciprocals of each other. Okay, now what? Wait a second. That's one of our identities for cosine. That's one of the 3 identities. So cosine 2 theta equals cosine 2 theta. That's our answer. So woohoo! That wasn't so bad after all. And I imagine that's probably going to be the case, that basically it's like, okay, use one of these identities, try to make some magic happen, you know, and see it through. Well, thanks so much for watching. Hope you enjoyed this video. Hope you will give it a thumbs up, because if nothing else, you like me or the video or both. Whatever you want to do is fine. And I'll see you in another video. Although if you are actually keeping up with me as I'm posting it, we're probably going to have a bit of a break before the next lesson because of Christmas and the holidays and that sort of thing. So I'll see you guys next time. Bye.